Let's talk about de Moivre. De Moivre's theorem says this: if I take a complex number in polar form r cis theta and I raise that number to the power of n, then I get r to the n cis n theta. Now, how did this come about? Well, you've actually seen this once before when we talked about powers of a complex number. So if I get a complex number like this one, and I go, let z be r cis theta, then z squared is r cis theta times r cis theta. And when I multiply complex numbers, I multiply the modulus, r squared, and I add the arguments, theta plus theta, which of course is 2 theta. Okay, what happens if I do it again? Z cubed is this, what I've already got, r squared cis 2 theta, times another z, r cis theta. So my rules for multiplying complex numbers tell me I have to multiply the modulus, r cubed, and I have to add the arguments. 2 theta plus theta is 3 theta. So if I keep going like this, surely I'll always end up with this. And in fact, it's possible to show that you do. The method we use to get there is proof by mathematical induction. Now, Year 11s, you haven't seen mathematical induction yet. Well, that's not quite true. If you've done some of the harder problem solving I've set you, you have seen it once or twice. But we haven't studied it as a formal method of proof. You'll do that next year. Nevertheless, watch how I do this proof so you can get some idea of what's going on with proof by induction. I won't actually ask you to prove this on an exam because it does involve mathematical induction, which you haven't done. However, next year you will need to apply de Moivre's theorem in a particular context. Year 12s, you have done proof by mathematical induction, and the syllabus does say for this unit that you have to be able to prove this. So at the end of your exam, they might ask you to prove this. So let's do it. By induction. So I want to prove this. I'm going to prove it for all positive integers n by mathematical induction. Okay? First step, let n equal 1. Well then, r cis theta to the power of 1 is indeed r to the 1 cis 1 theta, trivially, because it's actually r cis theta. So it's true for n equals 1. Okay. No, hang on. Assume true for n equals k. That is r cis theta to the power of k equals r to the k cis k theta. So I'm going to assume this is true and then see what happens for k plus 1. Consider n equals k plus 1. Well, r cis theta to the power of k plus 1 is equal to r cis theta to the k times r cis theta. What I've done is taken the plus 1 off into a separate factor. Well, this, though, by our assumption, is equal to this. R to the k cis k theta times r cis theta. by assumption. Okay, now I have two complex numbers and I'm going to multiply them. So I'm going to end up with the product of the matrices, which is r to the k plus 1, and I'm going to end up with the sum, I'm going to put a bracket in for the k theta, I'm going to end up with the sum of the angles, which is k plus 1 theta. But wait a minute, this is exactly what I need for my formula to work for k plus 1. Therefore, if true for n equals k, then it's also true for n equals k plus 1. So let me explain the reasoning here for the benefit of the Year 11s. I have shown that it's definitely true for n equals 1. And I've shown that if it's true for 1, then it's true for 2. And if it's true for 2, then it's true for 3. And if it's true for 3, it's true for 4, and so on. So I have actually proved that it's true for every positive integer n. Therefore, r cis theta to the n is equal to r to the n cis n theta for all positive integer n. Year 11s, please stop listening now. That's enough proof by induction for you right now. Year 12s. It is possible to prove that de Moivre's theorem holds not just for positive integers, but for all integers, including negative ones. And in fact, it's possible to prove that it's also true for rational powers. Now, that is beyond the syllabus. But if you're interested, I'm going to provide a proof for negative integers and also for rational numbers. My suggestion is you first try to prove it yourself and then have a look at those proofs.